What if you funneled Niagara Falls through a straw, the ultimate flow challenge? You're standing at Niagara Falls, watching 45 million gallons of water thundering over the edge every single minute. The raw power is mesmerizing. But here's a wild thought experiment that'll make your brain hurt. What if you could somehow funnel all that water through a single drinking straw? This isn't just a silly question. It's a physics nightmare that reveals just how extreme nature's forces really are. The numbers we're about to crunch will make you appreciate why engineers spend years designing proper water systems and why Mother Nature doesn't mess around when it comes to moving massive amounts of water. Think about it. Every second, 2,832 tons of water crashes over those falls. That's the weight of about 1,400 cars plummeting down every single second. Now imagine trying to squeeze all that through a tube the width of a pencil. The physics gets absolutely bonkers. The mind-bending mathematics. Let's start with the basic setup. A standard drinking straw has a diameter of 6 millimeters. That gives us a cross-sectional area of just 0.0283 square millimeters, basically the size of a pinhead. Now, during peak tourist season, Niagara Falls pumps out 2,832 cubic meters of water every second. When you do the math, forcing all that water through our tiny straw would require the water to move at 100,161,511 meters per second. That's over 224 million miles per hour calculated. To put this in perspective, this water would be moving at 1/3 the speed of light. Yes, you heard that right. 1/3 light speed. This isn't just fast. This is break the laws of physics as we know them. Fast! The water would be moving 292,000 times faster than the speed of sound. At these velocities, we're not dealing with normal fluid dynamics anymore. We're in the realm of relativistic physics, where water molecules would start behaving like particles in a cosmic ray shower. But the velocity is just the beginning of our problems. The pressure requirements are even more ridiculous. Using Bernoulli's equation, the dynamic pressure needed to achieve this flow would be approximately 50 trillion atmospheres calculated. For comparison, the pressure at the center of the Earth is only about 3.6 million atmospheres. We'd need pressure 14 million times greater than what exists at our planet's core. The energy requirements are equally absurd. To maintain this flow, you'd need 14.2 million terawatts of power. That's 710 million times more energy than the entire planet consumes. You'd need to harvest the complete energy output of several stars just to keep the water flowing. What would actually happen? Of course, none of this could actually occur in reality. Physics has some pretty firm rules, and our straw scenario violates most of them. But let's explore what would really happen if you tried this experiment. First, the straw would instantly vaporize. At the pressures we calculated, the molecular bonds in plastic would snap like rubber bands. The straw material would undergo explosive decompression, turning into a plasma cloud faster than you could blink. Even if we had some magical, indestructible straw, the water itself couldn't handle these conditions. At such extreme velocities, water molecules would start breaking apart. The hydrogen and oxygen atoms would separate, creating a stream of superheated gas instead of liquid water. We'd essentially have a hydrogen-oxygen torch hot enough to melt through solid rock. The sound alone would be catastrophic. Moving water at 292,000 times the speed of sound would create a sonic boom that would shatter every window within hundreds of miles. The acoustic energy would be powerful enough to level entire cities. But here's where it gets really interesting from a physics standpoint. If we somehow had the technology to create these conditions, we'd essentially be building a relativistic water gun. The water stream would carry so much kinetic energy that it could punch holes through mountains. Each water molecule would hit its target with the force of a high-energy particle accelerator. The real-world applications of understanding these extreme scenarios help engineers design better systems. For instance, knowing how fluids behave under pressure helps design everything from fire hoses to spacecraft fuel systems. NASA uses similar calculations when designing rocket nozzles, where they need to control the flow of superheated gases at extreme pressures. Water treatment plants deal with much more modest versions of this problem. They need to move millions of gallons through pipes efficiently without creating destructive pressures. A typical fire truck pumps water at about 1,500 gallons per minute, which requires careful pressure management to avoid damaging equipment or hurting firefighters. The Niagara Falls power plants actually harness a fraction of this energy safely. The Sir Adam Beck generating stations and the New York State Power Authority plants divert about half the fall's water during non-tourist hours. They generate approximately 4 million kilowatts of electricity, which sounds impressive until you compare it to our theoretical straw scenario that would require 14.2 million terawatts. Even nature has limits. The fastest recorded water flow in rivers reaches about 25 miles per hour in extreme flood conditions. Rapids above Niagara Falls max out at 40 kilometers per hour, and the water speeds up to 68 miles per hour at the falls themselves. These are already dangerous velocities that can easily kill a person, but they're still 3.3 million times slower than our straw scenario would require. The closest real-world equivalent to our thought experiment might be high-pressure water cutting systems used in industry. These systems can cut through steel using water pressurized to 90,000 pounds per square inch, about 6,100 atmospheres. That sounds extreme, but it's still 8 billion times less pressure than our straw would need. If you really wanted to move Niagara Falls' water through straws, you'd need approximately 100 million standard straws working in parallel to maintain normal water velocities. Even then, you'd need massive pumping systems to overcome the friction losses in all those tiny tubes. Funneling Niagara Falls through a straw isn't just impractical, it's physically impossible. The scenario breaks fundamental laws of physics and would require energy resources that don't exist in our solar system. But thinking through these extreme examples helps us appreciate both the incredible forces in nature and the ingenious engineering solutions humans have developed to work with water safely and efficiently. The next time you're sipping through a straw, remember you're using a precisely engineered system. That 6mm tube is perfectly sized for human lung capacity, which can generate about 1.5 psi of suction pressure, just enough to lift a drink a few inches, but nowhere near enough to handle the fury of Niagara Falls.